everyone. I'm Brittany Enos. I'm with the National Renewable Energy Lab. Thank you all for joining us today. We're going to have an awesome talk on how to use the cloud for continuous pump efficiency monitoring for irrigation districts and municipalities. Our speakers today are John Peers, who does sales, business development, and market research at XIO, and Moritz Both, who is the CTO at XIO. And just as a note, we are recording today's session. So if you don't feel comfortable being on camera or being recorded, just turn off your cameras. And then if you guys have any questions throughout the presentation, feel free to enter them in the chat box at any time, and they'll either get to them during this session or at the end, whatever ends up working better. So yeah, just enter whatever thoughts pop up in there and we'll get to them eventually. And with that, I will let you guys take it away.
Great, thank you so much. So my name is John Peers. I've been with the XIO team for about 5 years now. And I'm really going to just introduce our technology so that you have kind of a rough concept of what we're doing in the water industry, and then let Moritz do kind of a deep dive into how we're helping water systems and cities save money and improve their operations. So I'm just going to launch into half a dozen slides or so. So we're a technology innovation company. We manufacture a device that essentially takes a very complicated controls cabinet, a SCADA cabinet, and shrinks it down to the size of a deck of cards. So it's easy to build, easy to configure. We've been doing this now for about almost 10 years and have hundreds of systems in California. So this is you can kind of get a sense of where we started up in Northern California, Sonoma County. There's dozens of little systems that use our technology. Also down in Ventura County, we've got some of the largest irrigation districts using XIO to turn on and off these massive groundwater pumps and control the distribution of water. We essentially take cabinets that have changed very little over the last 25 years, and we eliminate all that complexity with this device that we manufacture and have multiple patents on, which is connects to cloud servers rather than to a local supervisory control computer. So these computer rooms, so if you imagine the California water industry with over 7,000 water systems, and imagine all of those supervisory control computer rooms sort of fading away into history. We believe that this is sort of one of the best and first examples of how that transition can happen. So we eliminate these complex cabinets, and we eliminate the control rooms, and we replace them with our cloud servers. So this is a technology that is rapidly evolving. We constantly improve our server technologies for security, enhancing the security of the system, adding new features, and the ability for us to support water systems all over the state, all over the world, is unprecedented in the water industry, and also I think in the SCADA industry. So that's my introduction, and I'll look forward to helping answer questions as we go forward.
Thanks, John. So we're going to talk a bit about the cloud and how to improve the efficiency of pumping. And the only way that you can do it is by constantly monitoring what's happening and addressing that dynamically. John pointed out in the very beginning that the architecture, the basic architecture of the way people handled the SCADA systems in the past hasn't changed for many, many years. It's still the case. There are very good reasons for that as well. And every time we tend to forget that there are very good reasons for doing the things the way that they are being done is we see events like what happened at Oldsmar in February, where somebody tried to hack into their system and change the values of some of the disinfectant. We also saw a case in Target not that long ago where somebody had remote access to the HVAC system, and a worm or malicious software got implanted on the target network, and the rest is history. About 120 million customers lost their personal information. I'm the co-founder of and CTO of XIO. I started my career in South Africa, did a lot of work for the mines, especially in energy management. Unlike the United States and a lot of countries in Europe, South Africa is in this unique position that it has very, very little natural resources in terms of water. So there's no way that you can use hydroelectric power to quickly fill in the gaps if you need to fill some rapid demand. Only about 3% of the electrical energy in South Africa comes from the renewable sources. They've changed it a little bit with wind lately, but the result is that there was a lot of incentives for the end users to make sure that they flatten their demand, and that is where I sharpened my tool shed. I'm part of a very talented multidisciplinary engineering team, and what we do is design control systems for critical infrastructure. And this is where the contrast comes in, or the conflict, because on the one hand, we in the past, going back to the traditional architecture of devices, the operational technology and the information technology used to be separate things. But what we've seen lately is there's a demand based on our connected world that tries to change that, but didn't always keep up with all the potential consequences of that. So what I'm going to talk about today is I'll show you some of the examples of the benefits that you can have in the cloud, but also what is required from an engineering perspective to make sure that you still maintain safety and security. And if I talk about safety and security, it is holistically. It's not only like what we saw in Oldsmar, somebody trying to change the sodium hydroxide level from 100 parts per million to 11,000. It's also about providing the service that you need to on an ongoing basis, so that ransomware doesn't affect your system, or if it does, how can what can you do to mitigate those circumstances? So let's look at California's water and energy just for a second. So in California, the last time I saw a measurement, they used about 176,000 gigawatt hours of electrical energy just for the water sector in a single year. You see the results there that I got from the Public Policy Institute of California. That is a huge number. In any language, that is a huge number. What I also find very, very interesting is that 10% of the state's greenhouse gas emissions are attributed to water, 20% of the state electrical energy, and 30% of natural gas. And one thing I never considered in these calculations are the treating and the heating of water. So, or think about it this way is, since this is such a water scarce part of the United States, one of the ways that people tend to try and fill the gap of water supply is to do desalination. If you do desalination, it is not free. It is at a very high energy cost, because for these reverse osmosis processes to run, you need a tremendous amount of energy. So the interplay of energy and water is much, much bigger than what I anticipated first. So let's look at a very simple case study first, a very conceptually very simple thing. Um, People in the pumping world know this better than I do, is you have some efficiency curve and there's some maximum efficiency point. And then you have a specific head, and then you have some flow rate that you design the pump for. As the head changes, you move up and down this efficiency point. So normally, if everything is fine and works the way you plan it to do, you will always operate at this peak efficiency point. The reality is way different because pumps wear over time, the impellers wear, the bearings change, the physical conditions also change a lot. So you move around this peak efficiency point. What we also see is that as the aquifers get overdrawn and depleted as the season goes by, you may shift on this curve towards a way less efficient point. And as the rainfall season comes and the aquifers fill up, you shift to the other side. One other thing that we also see regularly is that people over-design these pumps by about 10 to 20% to take into account changes in the system performance over the years. The net result is you hardly ever work on this peak efficiency point. And this is what we've taken advantage of. Is we have this one customer in Southern California. It's a big agricultural customer. They've got 11 big wells. The smallest one has a 250 horsepower pump on it. And they have to supply irrigation water on demand. And they've got some an aquifer or just some temporary storage that they use in order to supply the water on demand. But the pumps do not all have to run at the same time. It just depends on the demand. So what you can see here is each pump, we've calculated a trigger level on the cloud based on the efficiency of the pump. A second thing that you will notice is that there is a value called the efficiency order. And the efficiency order is what we use on a daily basis. We calculate the energy intensity for each pump, and energy intensity just as the kilowatt hours required to produce 1,000 gallons of water. And based on that efficiency order, we prioritize the way that these pumps come on. And then finally, you can see people can take a specific pump out of service. The net result for this customer is we save them $58,000 in just energy costs last year. But it's not only that, it is everyone living in the area also benefited, because if you look back at the initial slide about the contribution of greenhouse gases, this is pure energy savings, the amount of kilowatt hours that they used by not sequencing the pumps randomly, but sequencing them based on a very specific algorithm that we deployed on the system. This is what it looks like. So you'll see there's a screen on this cloud-based SCADA system where a user can do their pump ranking. You can see the current value of a reservoir, and you can see there's a desired fill level for the reservoir at a specific spot. Then we also allow our users to change the level of increments where we want to schedule these pumps. And based on that, you'll see pump 4 was ranked to start first, pump 2 second, pump 8 third, and pump 11 and so forth. And based on the pump level increment that is derived from the demand, we only need to run 3 of these pumps. You can see the ranking was based on the energy efficiency calculations that was based on the previous day. So based on these values, That is how we schedule these pumps so that they always run the most efficient pump first. We also have user comments so that there's always a journal in place so that people can see who did what at what point. I just obscured the names there to protect the privacy of the customer. So let's get back to SCADA. What SCADA really is about. So there are many uses of supervisory control and data acquisitions. The first one is operations, is making sure that pumps run or disinfection happens when it needs to happen. There are some regulatory compliance requirements where I get, in California, we have to report, each well producer has to report how much water they've pumped on a daily basis every single month. And there may be some efficiency reasons. So if you look at the long-term data of the pump performance, you may want to calculate the efficiency of the pumps and see if there's a gradual decline. You know something is wrong, and you can adjust there. If we revisit each one of these, you'll see operations is all about the here and now. Is the pump running right now because it needs to run? Is there an active alarm because the disinfection isn't enough right now? So it's all about the here and now. So when you look at the typical approach and the design of SCADA systems in general, it is all about the here and now. Regulatory compliance and reporting is sort of an afterthought, but there is some provision in the support for that. And then efficiency, hardly ever. People do not necessarily use the information to extract what they need so that they can do continuous improvement on their sites. If we compare that to a cloud-based SCADA system in terms of functionalities, if we first look at the feature set, when somebody deploys a SCADA system, the functionality is fixed, the performance is fixed. If they want any changes, it'll cost them a lot of money. A cloud-based SCADA system grows continuously. Or look at it this way, is fairly recently when I bought a new car, they wanted to sell me a GPS, and I didn't want to buy the GPS because I know as I drive out of that parking lot, that map will be old because it's a DVD that I pop in the trunk and that contains my map. The other side of the coin for me is Google Maps, or the Waze application for Google, that not only gives me current maps, but it also gives me day-to-day and minute-to-minute information about the traffic density. That's, I think, a fair comparison between what happens in traditional SCADA systems. As we learn more about the systems of our customers out there, we improve our offering. As we improve our offering, all the customers just automatically inherit it in the same way as people just get all the traffic information from a Google Maps setup. The main data usage for traditional SCADA is pretty much day-to-day plant operations. On the cloud-based SCADA systems, it's the same, but it also contains a big analytical aspects. Extendability in traditional systems is the master-slave architecture really limits your ability to extend the functionality. And the cloud-based SCADA systems is we see that we have specific sites where we have information from many different vendors that seamlessly integrate into one system to provide a very holistic view of what is happening on any system. Interoperability, traditional SCADA, you see these very, very specific vendor silos, whereas on a cloud-based SCADA system, the approach is open and to say, we have an API, people with the correct access rights can access the API and use the information to improve their systems or for additional analytics. What's the driver for moving away from the old systems? And the driver is convenience. We've seen our world change a lot around us. I recall watching a TED presentation just the other day, somebody showing how you can take a screen, a touch screen, and zoom and rotate an image by pinching and rotating your fingers. And the crowd were really impressed with what they saw. If I look back at it today, that is just basic expected behavior. Anybody with a smartphone expects that behavior. If we look at our connected world, my interaction with banking, with applications that allow me to share the bill at a restaurant, those are the type of things that drive this need for people to interact with their SCADA systems. So think about efficiency. The fact that you don't have to drive to a specific site to verify what the reading is hugely advantageous. We've seen many disasters in terms of big fires in California lately, and people had to evacuate their environments, but didn't lose access to their SCADA system. COVID was another thing where we saw big repercussions. There's this case in San Jose Water where some of the operators contracted COVID very early in the epidemic, and it came at a huge cost to San Jose Water to keep their systems running while dealing with the COVID. But we also see it with other industries. Many other industries make it easy for people to access their information, but the traditional SCADA systems do not make it easy for people to do that. But here's the state of the union. If you just do a basic search on what is happening out there, we see this on a very, very regular basis. And that is the biggest concern. And it all comes from this traditional architecture. John Wise is one of the foremost minds in this area of operational technology and the security associated with that. So just to set the foundation, we've got sensors and motor controls, so basic I/O devices. Then there are smart devices like control valves and PLCs, the programmable logic controllers. Then there are communication protocols and human-machine interfaces. And then there's typically a master SCADA system that control all these devices. So it will get information from a sensor and then tell a motor what to do. The scary fact is that what Wise points out is here are just a snapshot of all the potential attack vectors in this IT, information technology versus OT, operational technology world. The main issues, lack of authentication. What we see is typical SCADA systems have one screen that assumes physical security, meaning that if somebody has access to an office with the master SCADA system in there, it also implies that they have access to make changes that they can make on the system. In a connected world, that is not valid anymore. There's a lack of authorization. So different levels of the organization do not have different logins. There's often just very limited access or logins to the SCADA system. Anybody with access can do on the system what they need to do. Lack of data security. There's no encryption, and there's very little regard for backups and protocols using backup systems. In terms of communication networks, we see insecure protocols. The predominant protocol in these control system networks is Modbus. It was designed at a time where there was no regard for cybersecurity. So it's a very simple master-slave protocol that allows it to be easily exploitable. But I'll get back to that later. And finally, there's insecure life cycles. And insecure in the fact that when you have to update so many subsets of the system, you may need a connection to a network. And if your workflow does not allow for security, then you're open for attacks. And then the big thing is that it is very, very easy to find these type of devices. There's this search engine called Shodan, and this is a screenshot of Shodan's front page, the search engine for power plants. And this is the scary picture, is you can go and search there, and I find my security cam at my house on Shodan. That is how easy it is. So if there is an exploit available for some of these devices, it is very, very easy to find the information and then really to attack the system. Now, if we look at traditional SCADA system and cloud-based SCADA systems in terms of security responsibility, if you look at the controllers, the physical devices, the water system operator in both cases is responsible for that. Traditional system, you need an on-site PC. It's again the water system operator's responsibility to look after that thing. Cloud-based SCADA system, you don't need a specialized PC. Any device with a web browser can perform the operations or give you access to your system that you need. Software maintenance, same thing, water system operator. Cloud-based SCADA vendor, it's their job to keep the software up to date and make sure that it doesn't have any known vulnerabilities in it. Backup and antivirus, same thing. In traditional systems, it's all up to the water system operator. In the cloud-based system, again, it's the task of the vendor to do that. Passwords, SCADA systems, water system operators, often we've seen it on a sticky note just right next to the computer. On a cloud-based SCADA system, it is individual user access. But then we also see a different side to this, is the government recognizes the real need and the danger associated with everything here. There are a number of executive orders. The first one is to improve critical infrastructure cybersecurity, and then there's a policy directive for critical infrastructure resiliency. But there's also a large number of emerging standards. Idaho National Labs initially was tasked to look after the cybersecurity for nuclear power plants. Subsequent to that, they've really expanded and recently in February published a book called Consequence-Driven Cyber-Informed Engineering. Well, with the read is to say that with proper design and approaches, you can mitigate a lot of the cybersecurity issues that we see out there. There's also ISA 62443 that talks about security risk assessment and looking at that through a lens of different security levels. The AWWA also has a wealth of information about cybersecurity in water. If we look at consequence-driven cyber-informed engineering, I really like their approach is because they say is assume the worst-case cyber attack. And if that happens and you're fully compromised, what do you do? If your job is to provide safe and an adequate amount of drinking water, can you still do that? And can you still do that may mean you may have somebody going on site with a walkie-talkie, telling somebody else what the reservoir level is so that they can run a pump in manual mode. The point being is it possible for you to run your system in a way that does not require something that can be compromised with a cyber attack? IEC 62443 does it a little bit differently. They say there are a couple of security levels, and it's all connected to the skill set of the person trying to get into it. The lowest level, it is just somebody accidentally logged into your system, got the information, and they're changing something, or somebody accidentally changed the value that they shouldn't have. Just big mistake. The second one is some cybercrime hacker Their skills are a little bit more advanced. Their motivation is low. They don't have a lot of means. Their resources is it's probably some isolated individual sitting in a dark basement somewhere. Where it gets really hairy is when you get to security level 3, where you get hacktivists and terrorists, and their skill sets are industrial control system specific. Their motivation is moderate, typically monetary, and they exchange tools. They're very sophisticated, and they often concentrate on ransomware. The most scary of them all is the nation-state systems, and we've seen a lot of them lately. Those can target industrial control systems specifically. Their motivation is high because it is about the disruption of business as usual in typically democracies like ours. It's a sophisticated campaign. Think about what happened to SolarWinds late last year. SolarWinds is a company that specializes in supplying the government, amongst others, with tools to detect cybercrime. And after 6 months, they discovered they got hacked. So where do mere mortals like we fit in if somebody that sophisticated got hacked? The only way that that could happen is with the support of a nation state with multidisciplinary teams to do that. Risk analysis, I think everybody knows this, is you start with saying what can go wrong and what are the consequences if it goes wrong, and how likely is it to go wrong? How do we mitigate this issue? And this is a moving target as well. So in California, if we look at, say, a sewage lift station, what can go wrong? The power can fail. That's one of the scenarios. What are the consequences if it goes wrong? You have a spill, and on top of that, you get an EPA fine. How likely is it to go wrong? Very unlikely. Or at least that used to be the case, right? We used to have a very, very stable power supply until we started having these issues with wildfires caused by the equipment of the local utilities in California. Now we have had 2 consecutive years where the power to the area where I live got cut off preventatively to prevent wildfires. So we lost power for a total of 7 days over the two periods. So all of a sudden, the risk of what can go wrong, meaning the power can go away, changed dramatically because it's much, much more likely. And the only way to mitigate that is to have at least some generators, mobile generators on standby or available for rental to mitigate this risk. So let's get back to these vulnerabilities. What happened at Oldsmouth in Florida? I mentioned the old architecture, and I just want to delve into that a little bit deeper. Right in the middle there, you've got a SCADA server, and the SCADA server sends a pull request to a programmable logic controller, the PLC there, and it responds to the poll. But it can also send a command, and the PLC will respond to a command. And on the left there, we may have remote access or a need for remote access. Here, right there, is one of the big vulnerabilities that we see. This command response is master-slave, so the PLC typically doesn't have any way to verify the origin of the information. In some cases, it may be something as simple as a very simple password or an IP address. But even that can be spoofed. So anybody that can get access to that communication network can exploit any vulnerability. And that's exactly what happened in the Stuxnet case that we saw in Iran's nuclear power plants about 10 years ago. A nation state accessed their system even though it was disconnected to the internet, used that interface between the SCADA server and the PLCs and reprogram the PLCs or the setting of the PLCs. The second part, big thing here, is the SCADA server itself. The software that it runs and the operating system is very open to vulnerabilities. And nowadays, the big thing, and this is what happened at Oldsmar, somebody used an application called TeamViewer, got remote access to the SCADA server, and it was as though that person was in the control room. And that is one of the biggest vulnerabilities that we see, because in the old days, as I mentioned earlier, people assume if you have physical access, you have rights to do what you need to do on the system. In this case, somebody got access to the system. It was not physical access, but it was as though that person got physical access. Cloud-based SCADA topology is way different. It typically consists of field installable units. John showed you that earlier. These are smart devices that were designed in the age of cybersecurity, and their connection cross radio networks don't use the standard baseband radios that we see in traditional systems. They use IP-based systems with encryption and protection that only the radios can connect to themselves. We often see a topology using a cell phone or maybe something like a satellite modem that will connect to the cloud. We also see environments where the topology on the right-hand side is very similar, radio connection between the different devices, but it's connected to the secure router that opens a secure VPN tunnel to the cloud to do whatever needs to be done on the cloud. That way, there's a very good demarcation between the customer internet and the router itself. One of our recent customers had a ransomware attack and lost everything in their system except the cloud-based SCADA system. So all their accounts, everything else got compromised, but using this topology in their environment protected the system from what we saw with the malware. The new system architecture used smart controllers that sent a heartbeat to what we call cloud augmented control. And here's the difference. The smart controllers are reliable and fault tolerant, meaning they can work in the presence or the absence of the cloud. They will perform their task. If a tank level drops too low, they will start the pump. If the tank level gets to the full level, it will stop the cloud. It is when the cloud is available where we can do these advanced analytics, like the ones that I showed you earlier, that calculates the efficiency of the different pumps. There's also a historian, smart alarms, and then journaling, because journaling gives us the ability to say who did what, at what time, from where, and were they authorized to do that. But on top of that, there's this authorization and authentication to make sure that only people with the appropriate access rights can perform a specific operation. So some people may be able to look at reports, other people may be able to define reports. Some people may be able to run a pump, other people may not run a pump. They can only look at a specific alarm. So approaching this from cyber-informed, consequence-driven engineering, one of the things is right here where it's different than the case of traditional systems. Instead of just allowing people to change set points to whatever level they need to, we have the ability to limit that and to put those limits in the control device. So going back to the case of Oldsmar, in Oldsmar, they changed the sodium hypochlorite level from 100 parts per million to 11,000. The controllers, the smart controllers, now can have limits that says you're not allowed to have a value outside a range of, say, 50 to 250. That way, even if somebody maliciously breaks into the cloud or accidentally changes a value that is beyond the limits, the controller would just ignore that. The second part of this picture is this journaling, because the journaling also says we can use location awareness of systems to say, if you happen to be calling from the Ukraine or somewhere like Iran, it is most likely not the water operator trying to change the level. Therefore, we'll ignore the transaction. So finally, the customer access is secure, just as secure as any modern internet-based system would be. And here's the fundamental difference, right? Is on the right-hand side in the traditional systems, the SCADA system on the right always sends a command. The traditional field device responds to the command, and without really knowing where the command originated. With our system, the field installable unit always initiates the transaction, sends a heartbeat to the cloud. The cloud can then respond with a command. For me, the easy handle on this is, if I call you, you may get my caller ID, but you're never sure that it is me who called, because my caller ID can be spoofed. If, however, you call me and you recognize my voice when I answer the phone, you know unambiguously that you're speaking to the right person. This is the same principle that applies here. So coming back to how is this practical? So if you have an architecture that allows you to work in a secure environment, that also allows you to move beyond the here and now day-to-day operations that typical SCADA focuses on, you can do a tremendous amount of additional analytics that is really useful and saves a lot of money to the end user. So here's an example, a case study of one of our customers. The human eye is an amazing thing, because right there you can see a change in the slope of the water consumption of the tank. So obviously something bad happened here. And here down a little bit further on the 15th of August, you see another slope change. There's some ripples there. That's where some pump tried to keep up with a leak. Long story short, turns to be a massive, massive leak in somebody's system here. Easy to pick up with the eye. But if you don't have somebody looking at all these graphs all the time, it's very difficult to detect that. Our analytics engine is, we have something that uses signal processing techniques that is what we call a virtual flow meter. And here you can see that initial event took place, and within 15 minutes, we sent the customer an alarm saying, something is wrong with your system, you may want to go and have a look at that. What makes it a little bit tricky, though, is that if you look at the water usage at this site over a year period, you see that something that is normal use in the summer, it will definitely be a leak like what we see on February the 7th here. But the two leaks that I'm talking about was round about August and round about September. And what they finally did is found this after about a week of searching, 8 feet underground in a dry riverbed. One of the pumps got compromised. Compare that to a traditional system where the only way that you would notice it is maybe if you see the pumps run a lot, or the tank may get empty, or if the leak isn't that big, after the next billing cycle, you get your electrical energy bill. So a huge change in the value, because what we've saved here is not only a lot of operational cost, disaster money that these people accumulated over the time, because it took them so much shorter to find the leak, but also all the energy that would have been wasted over a long time until they finally realized that there was a leak in the system. So coming back to how the design and implementation in systems differ, the first one for the traditional system is the operational world trusted everything on the network explicitly. Everything on the network is supposed to be there. We're just going to assume that everybody can do what they need to do. On a cloud-based system, we say we're on the cloud. There's zero trust. We don't trust anybody. There's a fundamental difference there. The main concern for the traditional system is making sure the process runs the way it is and that the equipment is safe. On top of that, the cloud-based SCADA system is also really concerned about vulnerabilities and the ever-changing nature of vulnerabilities. The communication system on traditional system is deterministic. It's always there, it will always be there. In our case, we cannot assume the cloud will be there. It's very non-deterministic. Therefore, the system has to be designed from the onset with resiliency in mind. The threat focus, traditional systems, little or no regard, whereas with cloud SCADA system is there is an advanced adversary out there, and we have to constantly keep up with it. The security focus, again, is reliability and safety. In cloud-based system, it also includes malicious attacks on the system by other agents out there. These are some examples of journaling. I'm not going to delve into detail about that, but backups is another example of resiliency. I often ask people at conferences, do you think backups are good things? They say, yeah. I say, so how many of you have done one in the last week? And you'll be surprised how few they were. In a cloud-based system, because everything is automated, it just happens. It's just part of the DNA of a system. Disaster recovery, we test it regularly. The last time we tested with a fairly inexperienced engineer, we started from scratch. It took us 22 minutes from scratch to get the system back online. Typically, we have had outages that lasted less than 90 seconds. That is the norm. When we do a switch over, it's less than a minute if one of the systems fail, because they are really redundant in the way that they approach these the system. So in summary then, is on the one hand side, there's no security for any system, and that is pretty much suicide. On the other side, there's perfect security, and that's impractical, as the events in Iran showed us. The system wasn't connected to the internet. Despite that, their system was compromised. Remote access poses a significant risk, and we believe that cloud-based SCADA system gives you that perfect balance to not only do the job that you need to do, but also have these value-added systems where you have analytics that can improve the process, that can improve everything that we do for everybody involved, for all the stakeholders, like all the inhabitants of California, because we can save greenhouse gases, we can use less energy, and we can be smart going about it that way. I've got a couple of resources here in terms of security, password strength, and all kinds of other things. But with that brings me to questions and answers. And I think the most important takeaway is what happens if the cloud goes away. I know what we've done is we've designed the system assuming that that will happen. So the question then is, what happens if your SCADA system fails? How long will it be for you to recover and be back online? So with that, if you have any questions, please type them in. The chat event, Jennifer made a comment, it is scary. It is scary beyond reason. And that's the thing that keeps me awake at night, is we don't know what we don't know, right? Because how can we, as a relatively small company, compete with nation states out there? The answer is we can't. So what we assume is we assume that somebody already broke into our system, And it's our job to find that, rather than say it is not going to ever happen. But I think the big advantage for me having a cloud-based SCADA system is that you can amortize the learnings from each system and spread it out, and all the other people that is part of the system benefits from that, as is the case with Waze. If I drive down the freeway and say there's a pothole on the freeway and I mark it on my Waze system, people see that as well. Jennifer asked to post a link to the case study in the chat. Please email me. Let me share my screen again. I can send you some case studies. Unfortunately, we don't have the detailed case study published on our website yet, but as soon as that is available, we can email that to you. Any other questions?
Actually, do you mind if instead of just it's more of a dialogue question, do you mind if I don't put it in the chat? One, nice to meet you. Thank you for this presentation. I thought it was really interesting. I know that cybersecurity really is becoming something that everyone is really starting to focus on more and more for obvious reasons. And I put it was scary in the chat because literally one of the examples you gave, I was just like, that is not great.
Yeah.
It is horrifying, and I wouldn't even think to look for something like that. So that just goes to show how naive I am, right? But so related to that, I feel like as a NAWI Alliance and the community that we're generating, I feel like cybersecurity is probably something that we haven't yet flagged enough as kind of a discussion topic and a point of conversation. And so I'm just wondering if, for your feedback, if that would be something that would be valuable for us to add to the community website, so that, for example, when your case study is published and live, that you could post the link there and generate discussions and have people start, really thinking about it more, so that it's at the forefront of everybody's minds. Because I feel like if we're not flagging it, we need to flag it. That's how I feel. Tell me if I'm wrong.
No, on the contrary, I think you've barely scratched the surface there. It is of the utmost importance for us to flag it, right? So see what happened at Oldsmart is they had a choice. They could say, oh my goodness, this is embarrassing. We're not going to tell anybody. But they didn't. I think they did the right thing, because ultimately some operator was wide awake and saw what happened. They published it, and all of a sudden it is a wake-up call. The scary thing is the number of people that didn't publish that. That's the scary thing, because if you look at so the blue team is, oh, secret, we don't want to share information because it's embarrassing. The red team says, hey man, you go on the dark web, you pay a couple of bucks, you can get the tool, you can use the search tool to find that information. So with that said, I think it is of the utmost importance for us to share experiences. My view on cybersecurity has made probably a 180 in the last 3 months, and I've spent most of my career on it because it is such a rapidly changing field.
Yeah, and I would say too, I think it engenders trust if people are honest about saying, hey, we encountered this problem, we're looking for ways to address it, help us do better. So,
indeed,
I think that's really important.
Thanks for having us, you guys. I'm going to have to run.
No worries. And actually, I kept us over, so that is completely my fault. I'm so sorry. Brittany, sorry. It's my fault.
No, it's all good. It's all good.
All right.
Well, thank you guys so much for your wonderful talk.